In this lesson, we're going to be talking about the properties of exponents and radicals. So we have our product of powers, which states that if I am multiplying two things that have the same base, I'm going to take those exponents and I'm going to add them together and keep that base of a. The quotient of powers, which states if I am dividing two things with the same base, I'm going to take those exponents and take the top exponent and subtract the bottom exponent while keeping that common base. The power of a power, which states if I have something raised to a number and then raised to another number, I'm going to multiply those two numbers together. The power of a product, if I'm multiplying two terms within the parentheses, I can raise those both to this power. So I have a to that power and b to that power. And then the negative exponent, which states in order to get rid of a negative exponent, I'm just going to flip this and it would be 1 over a to the m. All right. So we're going to rewrite each expression using those properties of exponents, and we are not going to include any fractional exponents. So in the end, if we have fractional exponents, we're going to convert those into radicals. So I see that I have a base of 81 times another base of 81. So I will keep the base of 81. And I'm going to take those two exponents and I'm going to add them together. So 5/6 plus a negative 1/3 gives me 1/2. And I know that a 1/2 power is a square root. So really this is the square root of 81, which is 9. All right, on number 2, I could do this a couple of different ways. First off, I could go ahead and take this x and raise it to the 2/3 power, the y to the third and raise that to the 2/3 power, this x to the 1/2 and raise that to the 2/3 power. I could do all of that, okay? Or what would be a little more simple is to take what is inside the parentheses, that fraction inside, and reduce it if I can. So I have an x to the first divided by an x to the 1/2. That would give me x to the 1 minus a half. Since we're dividing, we subtract. And then I have that y to the third raised to the 2/3. So I'm going to simplify that. 1 minus 1/2 is 1/2. So I have x to the 1/2, y to the third to the 2/3. So now I have a product inside here being raised to a power. So I'm going to take each of these inside and raise them both to the 2/3 power. So if I have x to the 1/2 and I raise that to the 2/3 power, and then I have y to the third and I raise that to the 2/3 power, now I have a power to a power situation. So I multiply the 1/2 and the 2/3. That gives me 1/3. And then I take the 3 times the 2/3 and that gets me 2. And I see that I have a fractional exponent. It told me it didn't want a fractional exponent. So since this is a cube root, I'm going to write this as the cubed root of x to the first power. So I don't need to put the 1 there. And then I have a y squared. Now this is kind of backwards. We like to list our root back at the back. So y squared times the cubed root of x. All right, number 3. So there's nothing that I can reduce in the parentheses like on number 2. So I'm immediately going to take 3 and raise that to the 1/2 power. And I'm going to take the 32 to the 2/5 and raise that to the 1/2 power. So on top, that's just the square root of 3. And on bottom, I'm going to take that 32 and I'm going to raise it to the 2/5 times the 1/2. That would be 2/10, which is 1/5. So I have the 5th root of 32. 32 is a perfect 5th root. It is 2. And then I can't reduce, so I am left with square root of 3 over 2. All right, number 4. I have a situation here where I have something on the outside of the parentheses and then my parentheses and then an exponent. So order of operations tells me that I have to deal with the exponent first. So that's what we're going to do. So I'm going to leave this little 2a to the 1/3 out here. So I'm going to take a to the 2/3. And I'm going to take b to the 1/2 to the 2/3, which means I multiply. So 1/2 times 2/3 is 1/3. Now, this is not like a distributive kind of situation here. I don't have like a plus in between my two things to distribute out here on the outside. I really don't need the parentheses anymore, actually. So this is 2a to the 1/3 times this one term, which is a to the 2/3, b to the 1/3. So I'm going to go ahead and combine these two because they have the same base. So when I am multiplying two things with the same base, I add the exponents. So 1/3 plus 2/3 is 3/3, which is 1. And then I have my b to the 1/3. Again, we're not going to keep any fractional exponents. So this is the cubed root of b. So I have 2a times the cubed root of b to the first power, but I don't need to write the first power. All right, we're going to assume that all of the variables are positive on these, and we're going to do each little individual part separately. So I'm going to think of this as the 4th root of 81, the 4th root of a to the 8th, and the 4th root of b to the 5th. Now, 81 is a perfect 4th root, so I don't need to do a factor tree for that. A to the 8th is also a perfect 4th root because I know that 8 will divide by 4. And then I have b to the 5th. So I like to wait and do all of my roots at one time so that I don't get bogged down. So 5 will not divide by 4. And if your power is bigger than your root number, you can split it up and reduce this, like kind of simplify it, I guess. All right, so I'm thinking about how many 5s that is. Or how many b's that is. I have 5 b's. So I'm going to shave one off, and I'm going to say, does b to the 4th, is that a perfect 4th root? And it is. So I'm going to use 4 b's to make my perfect 4th root, and that will leave me with 1 b left over. So I have 4 b's and 1 b. That gives me my total of 5 b's. Then I'm going to go through and I'm going to root all of the perfect ones first because we want those in the front. So the 4th root of 81 is 3. The 4th root of a squared is, or a to the 8th is a squared. The 4th root of b to the 4th is b, and then you have your 4th root of b. All right, so I'm going to take a look at number 6. Now I'm going to have to take the cube root of the top and the cube root of the bottom. But if I can reduce before I do that, then it might be beneficial to me. So I see that I have an x to the 4th divided by an x to the 1st. So if I thought about this, x to the 4th divided by x to the 1st, that would be x to the 3rd. So I'm going to go ahead and reduce that. So now I have x to the 3rd, y to the 2nd over 125. So I'm going to cube root the top. So I'm going to cube root my x cubed. I'm going to cube root my y squared. And I'm going to cube root my 125. So x cubed is a perfect cube. So the cube root of x cubed is x. My power here on the y is smaller than my root number, which tells me there's nothing I can do with that. I'm just going to leave it as the cube root of y squared. And the cube root of 125 is 5. All right. Number 7 is more of like an exploratory problem. We're not going to have an actual answer in the end. It's just kind of demonstrating the product property of radicals so that we can kind of see how they work. So I could think of this as ab to the 1 over n. All right. And then I could think, well, I have a product, so I can raise both of those to that power. So this is a to the 1 over n and b to the 1 over n. And then I can say to myself, well, if I have an n on bottom, that's an nth root. So this is the nth root of a times the nth root of b. And then because I have an nth root times an nth root, that would give me the nth root of ab. And now we have full circle came back to what we originally had. And that concept that is listed down here is exactly what that property is talking about. And it works the same for the quotient property. All right. So number 8, we're going to cube root the 16. And we're going to cube root the x to the 5th. So 16 is not a perfect cube, so we're going to do a factor tree for 16 to kind of help us out. So we have 2 times 8. 8 is 2 times 4. 4 is 2 times 2. So I have 2 to the 4th. And I have to think to myself, how many of those 2's will make a perfect cube? Well, go backwards. Will 3 divide by your root of 3? Yes. So I can split this into 2 cubed, which would leave me with 1 2 left over. All right, I have 5 x's, so I need to split that into 2 terms. How many of those 5 x's will make a perfect cube? So I'm going to go down through the line. Will x to the 4th, is that a perfect cube? No. So I go x to the 3rd. That is a perfect cube. And that would leave me with 2 x's left over because I have to have the 3 plus the 2 to give me 5. So do your perfects first. Cube root of 2 cubed is 2. The cube root of x cubed is x. And then I have the cubed root of 2x squared. All right, what is the reduced radical form of each expression? Assume x is positive. All right, so I'm going to multiply these together. If I have 2 roots that I want to multiply together, they have to be like radicals. So I have a 5th root of 16 times a 5th root of 8. So I can take and multiply the 16 and the 8 and put that together underneath the root. That's 128. So now I'm going to do a factor tree for 128. So I have 2 and 64. 64 is 2 and 32. 32 is 2 and 16. 16 is 2 and 8. 8 is 2 and 4. And 4 is 2 and 2. That gives me 1, 2, 3, 4, 5, 6, 7 2's. Now, how many of those 2's will make my perfect 5th root? Well, 6 does not divide by 5, but 5 does divide by 5. So I'm going to do the 5th root of 2 to the 5th. And because I had 7 of them and I just used 5, that leaves 2 of them left over. So the 5th root of 2 to the 5th is 2. And then I have the 5th root of 2 squared, but we need to simplify that. 2 squared is 4. Now, I see on number 10, I do not have the same root. I have a 6th root and I have a cube root. So I need them to be the same root. So we're going to manipulate them a little bit. So I'm going to think of this as 8x to the 1/6 times 2x to the 1/3. Now, I need a common denominator so that I can put these roots together. I see that I have a 6 and a 3, so I can get a 6 over here if I multiply by 2 over 2. I'm going to kind of leave this left part just kind of hanging until I get done with this right side. So that would give me 2/6. Now, I want this to be a 1 on top, so I can think of this as 2 times 1/6. Well, if I am multiplying those, I could have had a power to a power situation. In other words, maybe this 2x was raised to the 2 and then raised to the 1/6. Okay, so I'm going to kind of pull the 2 off the top and I'm going to square the 2x. 2x squared is 4 and then x squared, and I'm raising that to the 1/6. And now I can go ahead and put this other side over here. So now I have them both raised to the 1/6. I can multiply them together. So 8 times 4 is 32. And then x to the first times x squared is x to the third. And this is to the 1/6 power. So remember, this is a 6th root of 32x to the third. Now, 32 is made up of 5 2's. So I don't have 6 of anything that I could split that into. And I also only have 3 x's. So there's nothing more I can do with that one. All right, number 11. So if I can reduce inside my root, I would do that. I can't reduce, so I'm immediately going to cube root my top and cube root my bottom. But I can see that 9 is not a perfect cube. 9 is made up of 3 times 3. That's only 2 terms. I need 3 or more of something to be able to reduce. So I can't reduce, but I have to get this root off the bottom. So I need to find a way to make this a perfect cube. So I'm going to have to multiply by something. So let's think about this. I know that the very first perfect cube is 1. 1 is a perfect everything, so we're going to kind of ignore 1. But my next perfect cube would be 2 cubed. So 2 times 2 times 2, which makes 8. So my first perfect cube is 8. There is nothing that I can multiply by 9 to get 8, like no integer. So I'm going to go to the next one, which would be 3 cubed. And then it would be 4 cubed and 5 cubed and 6 cubed. I wouldn't skip any if you're searching for your perfect cubes. All right, 3 cubed is 27. So is there a way I can multiply by 9 to get 27? Yes, there is. So I'm going to multiply by a cubed root of 3 because 9 times 3 is going to give me 27. But I also have an m. I have an m to the first. So I need 2 more m's to make 3 m's to make the perfect cube. So I'm going to multiply by an m squared as well. So we have to do that on top and bottom. That way we're not changing the value, we are just changing how it is written. So I have a cube root times a cube root, so I'm going to multiply those together. That gives me 2 times 3 is 6, and then n and m squared, over, multiply across, 9 times 3 is 27, m to the third. This should be a perfect cube because you multiplied by this to make it a perfect cube. All right, so let's go ahead and cube root that denominator. The cubed root of 27 is 3, and the cubed root of m to the third is m. Now you do want to check your top and make sure you can't reduce that. 6 is made up of 2 times 3, so we don't have 3 of anything. We only have 1 n, and we only have 2 m's. So there's nothing that we can do to reduce that any further. So we're going to do the same thing on number 5. Look to see if you can reduce first. You cannot, or not number 5, sorry, number 12. All right, so we have the 5th root of 7, and then we have the 5th root of 16x to the third. All right, so I know that 16 is not a perfect 5th root, so I'm going to start with my first perfect 5th root, which would be 2 to the 5th. 2 to the 5th is 32. Is there something I can multiply by the 16 to get that 32? The answer to that is yes, I can multiply by 2. So I'm going to do that on top and on bottom. And then I have 3 x's, but I need something that divides by 5. So I go up to 4. That's not enough. Up to 5. That gives me my 5 x's. So I need 2 more x's with that. So we'll multiply across. 7 times 2 is 14. X to the second. All over. The 5th root of 16 times 2 is 32, x to the 5th. And remember, this should be perfect because you made it that way. So we have the 5th root of 14x squared all over the 5th root of 32, which is 2, and the 5th root of x to the 5th, which is x. And now you don't have that root in your bottom, and you are good to go. Again, always make sure you check the top to see if you could reduce that. All right, so I'm multiplying radicals again, but I have a 4th root and I have a square root. So this is kind of like number 10, where we need to find a common root, I guess, for lack of a better phrase. So we have 27x to the second to the 1/4 times 3x to the 1/2. So I can get a common denominator of 4 by multiplying by 2 over 2. That's going to give me 2 over 4, and I can view that as 2 times 1/4. So I'm going to take that 3x and square it and then raise it to the 1/4. That's going to give me 9x squared to the 1/4. And over here I have 27x squared to the 1/4. So now I have a 4th root for both of these. I'm going to take the 27 times the 9. That gives me 243, and x times x, or x squared times x squared, is x to the 4th, and this is both being raised to the 1/4 power, which is a 4th root. Now I do need to do a factor tree for that 243. 243 is 3 times 81. 81 is 9 times 9. 9 is 3 and 3, and 3 and 3. So I have 3 to the 5th. So if I'm splitting this up, I know for this for this fourth root, I'm going to need 4 of these 5 to divide by 4, which leaves me with one of the 3's left over. And then I know that x to the 4th is a perfect fourth root. So my perfect fourth roots would be the 3 to the 4th. So the fourth root of 3 to the 4th is 3. And the fourth root of x to the 4th is x. And then you have your fourth root of 3. All right, when you are adding radicals, you have to have like radicals in order to be able to combine them. So let's say that I had like x times the square root of 3. Okay, and I had a 2 in front of that. Let's say that. Behind this coefficient, that would have to be exactly the same if I wanted to combine it with another term. So if I had 2x squared to 3 and a 3x squared to 3, I could put those together. But the second that I change one little thing, like make that an x squared, I can no longer put them together. They're not like radicals. So in order to know if they're like radicals, then I'm going to have to do my factor trees, and I'm going to have to reduce them. So I'm going to take 20 and do my factor tree. So 20 is 2 times 10. 10 is 2 times 5. So I have 2 squared and a 5. So 2 squared would be a perfect square. 5 would be the number that's going to stay under the root. So I have square root of 2 squared times the square root of 5. Then I'm going to do the same thing for 16. So 16 is 2 and 8. 8 is 2 and 4. And 4 is 2 and 2. So I have 2 to the 4th. Now I'm doing a cube root of 16. So how many of those 4 2's will make the perfect cube? And that would be 3 of them. So if I use 3 of them for the perfect cube, that leaves 1 left over. Then I need a factor tree for 250. 250 is 2 and 125. 125 is 5 and 25, and 25 is 5 and 5. So I have 5 cubed with a 2. So the 5 cubed is a perfect cube. So of the cubed root of 5 cubed, and then what I have left over there is 2. And then 5 is a prime number, so we can't do any splitting there. So if I take the square root of 2 squared, that's 2, and then square root of 5. The cubed root of 2 cubed is 2, and then I have the cubed root of 2. The cubed root of 5 cubed is 5 cube roots of 2. And now I'm ready to combine like terms or like radicals. So I have a 2 square root of 5 and a negative 1 square root of 5. That would be 1 square root of 5. And then negative 2 cube roots of 2 and 5 cube roots of 2, which gives me 3 cubed roots of 2. All right, number 15. So let's go ahead and do our factor tree for 2,000. 2,000 is 2 and 1,000. 1,000 is 2 and 500. 500 is 2 and 250. 250 is 2 and 125. 125 is 5 and 25. And 25 is 5 and 5. So we have 4 2's and 3 5's. So I'm doing a cubed root. So how many of those 4 2's are going to make my perfect cube? That would be 3, and that would leave 1 left over. And don't be like me and put the wrong root number out here. We're doing cube roots. All right, and then I have a 5 cubed, which is a perfect cube. All right, the square root of 2 is prime, so we'll leave that alone. And then 128 is 2 and 64. 64 is 2 and 32. 32 is 2 and 16. 16 is 2 and 8. 8 is 2 and 4. And 4 is 2 and 2. So that gives us 7 2. So how many of those make a perfect cube? Well, if I drop one off, that's 6. 6 does divide by 3, so 6 of these will make the perfect cube, and that leaves me with 1 left over. So the cubed root of 2 cubed is 2, and the cubed root of 5 cubed is 5, and we need to multiply those together, which makes 10 cubed roots of 2. Then we have this square root of 2. The cubed root of 2 to the 6th would be 2 to the 2nd, which is 4. So we have 4 cubed roots of 2. So I can put together the 10 cubed root of 2 and negative 4 cubed root of 2, which makes 6 cubed roots of 2 plus the square root of 2. All right, on number 16, we have already reduced the square root of 20 in a previous problem. That was 2 square roots of 5, so we'll just write that down. Let's do a factor tree for 600. So we have 6 and 100. 6 is 2 times 3. 100 is 4 and 25. 4 is 2 and 2. 25 is 5 and 5. So we have 3 2s, a 3, and 2 5s. So we're doing square roots. So how many of the 3 2s will make a perfect square? And that would be 2 of them. So that's going to leave 1 left over. Then we have a square root of 3. And then 5 squared is a perfect square. And then let's do 125. 125 is 5 and 25. And 25 is 5 and 5. So we have 5 to the 3rd. So we're going to use 2 of those 5s to make the perfect square, and then 1 left over. So we have 2 square roots of 5. The square root of 2 squared is 2. The square root of 5 squared is 5. So that gives us 10. Square roots of 2 times 3 are left underneath there, so that's 6. Minus, and then the square root of 5 squared is 5. Square roots of 5. We can put together the 2 square root of 5 and the negative 5 square root of 5, which will give us negative 3 square roots of 5, and then minus the 10 square root of 6. Now let's talk about multiplying. So I can multiply roots and multiply what's underneath them as long as they are the same root number. So I have the cubed root of 7 times 2 is 2 cubed roots of 7. The cubed root of 7 times the cubed root of, or a negative cube root of 49 is a negative cubed root of 343. This happens to be a perfect cube, and it's 7. So I have 2 cubed roots of 7 minus 7. And since 7 is a prime number, we don't have more than one of it, so we can't split that up into anything. Number 8, we are multiplying conjugates, and when you multiply conjugates, the middles should cancel out. So just be aware. So I have x times x is x squared. X times square root of 10 is x square roots of 10. Negative square root of 10 times x is negative x square root of 10. And a negative square root of 10 times a positive square root of 10 is a negative square root of 100, which is negative 10. So if I take a root times itself, it just ends up being what's underneath there, because it's like saying the square root of like 10 squared, which would be 10. All right, the two middle terms are opposites, and they're going to cancel out. So I'm left with x squared minus 10. All right, number 19, we have 2x times 2x is 4x squared. 2x times negative square root of 3 is negative 2x square roots of 3. Negative square root of 3 times 2x is negative 2x square root of 3. And square root of 3 times square root of 3 is negative square root of 3 times negative square root of 3 is positive square root of 9, which is 3. So we have 4x squared. Negative 2x square root of 3 and negative 2x square root of 3 make negative 4x square root of 3. And then plus 3. Number 20. Square root of 6 times 5 is 5 square roots of 6. And square root of 6 times square root of 3 is the square root of 18. We can reduce the square root of 18. So 18 is 2 and 9 and 3 and 3. So we get 3 squared and 2. So I have 3 squared is my perfect square, and 2 is my prime number. That gives me 3 square roots of 2. And then I have that 5 square root of 6 in front of that. And I can't combine those because they are not like radicals. All right, 21 through 24 are like the one where we had the root on the bottom, number 11. Okay, but the difference is that one was just a root by itself. It didn't have plus a number or anything like that. So when we have a root on bottom that's being added to another root or a number, we have to multiply by the conjugate to get rid of the roots on the bottom. So remember, a conjugate would be just change the sign in front of the root. You only change the sign of the root. So I don't like that there's this square root of 5 in the bottom. So I'm going to multiply by the conjugate of 2 plus square root of 5, which would be 2 minus the square root of 5. So on top, I'm just going to multiply across. 1 times 2 is 2. 1 times negative square root of 5 is negative square root of 5. On the bottom, we have 2 times 2 is 4. 2 times negative square root of 5 is negative 2 square root of 5. Square root of 5 times 2 is positive 2 square root of 5. And square root of 5 times negative square root of 5 is negative 5. These two middles should cancel out. So on top I have 2 minus the square root of 5. And then on bottom 4 minus 5 is negative 1. I can reduce that. 2 divided by negative 1 is negative 2. And negative square root of 5 divided by negative 1 is positive square root of 5. And everything is simplified. So on number 22, I have the conjugate of 2 minus the square root of 3 would be 2 plus the square root of 3. So we do that on top and bottom so that we're not altering what the value is, just changing how it's written. 5 times 2 is 10. 5 times the square root of 3 is 5 square roots of 3. Negative square root of 2 times 2 is negative 2 square root of 2. And negative square root of 2 times positive square root of 3 is a negative square root of 6. On the bottom, 2 times 2 is 4. 2 times the square root of 3 is 2 square roots of 3. Negative square root of 3 times 2 is negative 2 square roots of 3. And negative square root of 3 times square root of 3 is negative 3. These two on the bottom should cancel out. They always should go away. You have 4 minus 3 on bottom, which is 1. Nothing on top can be put together. We don't have any like radicals, no like terms. We don't have any roots that need to be simplified. So we just have 10 plus 5 square root 3 minus 2 square root 2 minus the square root of 6. And that was all over 1, so just the numerator. 23, the conjugate would be 1 plus the square root of x. So I have negative 4x times 1 is negative 4x. Negative 4x times the square root of x is negative 4x square roots of x. 1 times 1 is 1. 1 times square root of x is square root of x. Negative square root of x times 1 is negative square root of x. And negative square root of x times the positive square root of x would be negative x. The two middle and bottom cancel. There are no like terms on top. Nothing that needs to be simplified. On the bottom, we have 1 and negative x left over. All right, 24, it's better if you'll write this with the root at the back. That way you don't think about changing the sign in the middle. You always change the sign in front of the root. So we have a 3 plus the square root of 5. So our conjugate would be 3 minus the square root of 5. So square root of 7 times 3 is 3 square roots of 7. Square root of 7 times a negative square root of 5 is negative square root of 35. On the bottom, we have square root of 5 times 3 is 3 square roots of 5. Well, actually, let's do it with the, this one turned around. 3 times 3 is 9. 3 times negative square root of 5 is negative 3 square roots of 5. Square root of 5 times 3 is positive 3 square roots of 5. And negative square root of 5 and a positive square root of 5 make negative 5. The 2 in the middle cancel. On top, there's nothing to be combined. I can't reduce any of these. 9 minus 5 is 4.